Palm Jumeirah is not protected by the shape of a palm tree. It is protected by a ring of rock, exactly 11 kilometers long. But a 2023 study tested this exact coastal defense under higher future sea levels. In the modeled conditions, the existing outer rocks failed to meet the specific stability criteria used by the researchers, and the sheer amount of water crossing the crest exceeded the acceptable 100-year limit. This does not mean the palm is collapsing today, but is the sea forcing Dubai to redesign the very shield that made this construction miracle possible. Stretching roughly 5 kilometers into the Arabian Gulf, the Palm Jumeirah is a globally recognized symbol of modern economics and luxury real estate. It houses tens of thousands of residents, along with high-end hotels, marinas, and beaches. But what makes this entire ecosystem functional is the crescent. This 11-kilometer breakwater surrounds the inner fronds, acting as the primary barrier against the open ocean. It features 2 strategic openings to facilitate water exchange and vessel movement, but its main job is to absorb the brutal force of incoming waves, especially from the northwest. The luxurious resorts built on top of the crescent are just the visible layer. The functional defense, the element that dictates whether the marinas stay calm and the beaches remain intact, is the rubble mound structure beneath them. Hotels are not the first line of defense. The rocks are the first line of defense. If this 11-kilometer ring were to lose a fraction of its wave-absorbing capacity, which sector of the high-end dining and real estate market sitting right behind it would feel the pressure first? The luxury industry here operates in a strict dependency trap, relying entirely on an engineered perimeter to keep the fragile environment perfectly controlled. The tourism sector is highly sensitive. In recent years, global economic shifts have tested Dubai tourism with hotel occupancy, relying heavily on the illusion of absolute safety and perfection. Even a slight perception of vulnerability or an empty walkway at a premium location could trigger a tourism crisis, sending ripples through the broader economy. But the immense strength required for the crescent is restricted by another fundamental demand. The protective layer must remain low enough so that the people living and vacationing behind it can still see the ocean. To understand the vulnerability of this construction miracle, you have to look at how a revetment works. It operates in 4 distinct steps. First, an incoming wave approaches the sloped rock surface. Second, the rough, irregular shapes and the gaps between the rocks dissipate the energy of the water. Third, the individual stones must be heavy enough to resist being displaced by that massive force. Finally, any excess water that manages to crest the top is collected and routed safely back into the sea. It sounds straightforward, but the original design documents reveal a critical conflict. The crest of the crescent was kept relatively low. The developers and clients demanded an unobstructed view of the Arabian Gulf. A towering seawall would have blocked the horizon, completely destroying the premium value of the waterfront properties. Therefore, engineers could not simply build a higher wall to guarantee maximum protection. Subsequent studies have also maintained this strict condition, avoiding any solutions that involve raising the crest elevation. In my view, this is exactly what makes the crescent fundamentally different from a typical industrial breakwater. It does not just have to work flawlessly, it must also remain practically invisible to the guest experience. Could the very ocean views used to sell billions of dollars in real estate be restricting the ways that exact same real estate can be protected? The luxury market demands perfection. Guests paying premium rates do not want to look at an imposing concrete barrier. They want the endless blue horizon. This delicate balance becomes significantly more critical when the baseline water level creeps closer to a crest that nobody wants to raise. The core problem does not require a catastrophic storm to become evident. We just need to examine the concept of freeboard. Freeboard is the vertical distance from the resting water level to the top edge of the defense structure. When the baseline water level rises, that freeboard shrinks. The exact same wave now starts its journey much closer to the top. As a result, it becomes far easier for water to cross over the barrier. Deeper water conditions can also alter how waves approach the armor layer, increasing their impact force. A detailed 2023 engineering study examined multiple scenarios looking toward the year 2070. The detailed modeling utilized a highest baseline increase of 0.42 meters. In this scenario, the 100-year significant wave height was modeled at approximately 4.23 meters. For context, the original design from the early 2000s utilized a wave height of roughly 4.0 meters. The ocean does not need to generate a wave twice as high to challenge the system. It merely needs to raise the starting point of that wave closer to the crest. A few dozen centimeters might sound negligible on paper, but is it still negligible when it compromises the safety margins of an 11-kilometer-long defense line? The sheer scale of the infrastructure means that small percentages translate into massive real-world impacts. We must consider the modern economics of maintaining such a structure. The real estate market relies on absolute stability, and even minor increases in water volume crossing the barrier can trigger cascading maintenance costs. If the baseline shifts, the entire mathematical equation holding the palm together must be recalculated. This shift in the baseline parameters naturally leads the 2023 study to ask a much more direct question. Are the massive rocks currently sitting on the outer edge still heavy enough to handle the future? The most crucial component of this defense system is the armor layer. This is the outermost shield of rock that takes the direct punishment from the open sea. Currently, the existing armor utilizes rocks weighing between 3 and 6 tons each. However, when researchers modeled the future 100-year wave conditions, they calculated that the minimum average mass required for stability is approximately 8.1 tons. Because of this massive gap, the existing armor layer failed to meet the specific stability criteria used in the study. It is important to note that the lower toe of the structure still met the criteria. The internal filter layer also passed the test. The 8.1-ton figure does not mean every single rock must be immediately ripped out and replaced today. It is the mathematical outcome of a modeled future condition evaluated against strict engineering benchmarks. But it clearly demonstrates that the margin of safety could be narrowing as environmental inputs change. What stands out to me is not just how massive an 8.1-ton rock actually is. The truly remarkable part is how a relatively small shift in ocean conditions could eventually force engineers to reevaluate kilometers of heavy armor. Are the iconic fronds of the palm protected by a rock layer strong enough for the future, or merely strong enough for the era in which it was built? A tourism-dependent economy requires absolute certainty. If high-end visitors perceive that the infrastructure is constantly under repair, it damages the brand of the destination. This is the luxury industry dependency trap in action. The stability of these stones is the invisible foundation of the local economy. If the armor shifts, the confidence of global investors might shift along with it. But rocks moving out of place is not the only way a coastal defense structure loses its performance. Water can also find its way over the top. Overtopping occurs when incoming waves push water directly over the crest of a defense structure. It is vital to understand that overtopping does not mean the crescent has broken open or collapsed. Coastal defenses are designed to allow and manage a specific amount of water. The wide crest of the breakwater helps collect this overflow and channel it back into the sea before it reaches populated areas. However, when the volume of water exceeds the design criteria, the drainage systems and the properties positioned right behind the wall must endure significantly higher pressure. This situation can increase the risk of localized erosion, temporary flooding, or a partial loss of function in a specific sector. In the rigorous 2023 study, the strict limit set for a 100-year event was 1.00 liters per second per meter of the breakwater. When researchers calculated the future scenario using standard formula methods, the result reached approximately 1.63 liters per second per meter. When they applied an advanced artificial neural network approach, the volume climbed even higher, to about 2.05 liters per second per meter. Both of these calculations clearly exceed the critical threshold established for the study. Does a seawall only fail when it crumbles into the ocean, or does it fail the moment the water crossing it exceeds the exact volume it was built to control? This technical performance drop does not equate to current destruction, but it demands constant monitoring. The sheer volume of high-end real estate resting in the immediate vicinity means that any excess water is a direct threat to commercial operations. The dependency trap of luxury tourism means that even minor flooding could cause major reputational damage. In a city known for its pristine empty walkways and flawless presentation, the reality of overtopping introduces an unpredictable variable. It proves that the engineering requires active, continuous management rather than passive observation. This leads the conversation away from theoretical computer models and mathematical formulas. The Palm has already had to execute a massive real-world maintenance operation driven by a much more visible process: beach erosion. The Palm Jumeirah is not a static installation that can be built once and left alone. To maintain its flawless appearance, the island requires highly active management. This was clearly demonstrated by a massive beach enhancement project that began in 2022 and concluded in late 2023. During this intensive operation, crews treated approximately 55 kilometers of the island coastline. They pumped in roughly 1.5 million cubic meters of specialized marine sand to restore areas affected by natural erosion over time. The width and the gradient of the beaches were meticulously reshaped and readjusted to meet premium standards. We must be absolutely clear here. Pumping sand onto a beach is not evidence that the rock armor of the crescent has failed. Beach nourishment and revetment reinforcement are two entirely different categories of engineering work. The sand project is not one of the 3 upgrade options proposed in the 2023 study. However, its narrative significance is immense. It proves that the coastal system of the Palm already demands large-scale physical intervention. Sand is constantly moving, and the shape of the artificial coastline must be forcibly maintained. To be fair, to Dubai, routine maintenance does not equal a project failure. It is a standard procedure for artificial coastlines worldwide. But the sheer scale of the recent sand nourishment proves that artificial land cannot hold its shape forever without expensive help. If millions of cubic meters of sand must be added just 2 decades after construction, how will the financial cost of maintaining the Palm change as ocean conditions continue to evolve? Maintaining a flawless luxury destination is heavily reliant on this invisible maintenance cycle. The modern economics of such mega projects dictate that the initial construction cost is only the down payment. The ongoing operational expenses define the true price of the land. The economic burden of this continuous upkeep is massive, and it directly impacts the long-term viability of the tourism sector. And the beach maintenance only dealt with the soft sand. The 2023 revetment study proposed 3 major ways to physically alter the primary rock defense itself. To understand the true risk profile of this construction miracle, we need to redefine what engineering failure actually means. It happens in stages. Level 1 is a reduction in the margin of safety. The structure still stands, but it operates much closer to its maximum limit. Level 2 involves localized armor displacement, where specific blocks shift and must be manually replaced by cranes. Level 3 is an increase in overtopping, forcing the internal drainage infrastructure to handle a heavier load. Level 4 is beach erosion, demanding the costly addition of marine sand. Level 5 is a functional loss in a specific segment, leaving the properties directly behind it exposed to heavier wave action. Level 6 is catastrophic structural damage, where multiple defensive layers fail simultaneously. The current research does not provide any evidence that Level 6 is happening. The armor and overtopping metrics did not meet the modeled criteria, but the tow and filter layers remain secure. Beach maintenance has occurred, but the crescent is still holding back the sea. To me, this is exactly how a mega project becomes overwhelmingly expensive. Not because it vanishes overnight in a dramatic disaster, but because every single component must be constantly inspected, replenished, and redesigned before it actually loses its primary function. Does the sea truly need to destroy the palm, or does it just need to gradually increase the cost of keeping it stable, decade after decade? The economic reality is that the maintenance required to prevent a full collapse might eventually rival the cost of the original construction. The luxury industry dependency trap means developers must aggressively prevent even level 2 or 3 failures to protect the brand. The stakes are simply too high for passive observation. The entire system must be viewed as a living entity. Engineering solutions do exist, but none of them are as simple as just dropping a few extra rocks and walking away. The 2023 academic study outlined 3 preliminary design concepts to upgrade the crescent and potentially extend its design life by 50 years. These are conceptual models, not officially approved government contracts, but they reveal the sheer complexity of altering a live megaproject. Option 1 involves adding more armor and creating a gentler slope. By flattening the angle of the rock face, you increase the distance the wave must travel to dissipate its energy. This widens the crest and directly reduces overtopping. The trade-off is severe. It requires a massive volume of new rock, takes up significantly more space, and forces heavy construction right alongside operating luxury resorts, potentially disrupting the high-end tourist experience. Option 2 introduces a flat berm. This involves building a wide horizontal step directly into the slope of the seawall. The incoming wave loses a massive amount of energy crashing onto this step before it can even reach the top, allowing the crest to remain low. The primary downside is that it alters the exterior footprint, requires substantial new materials, and demands intense stability testing to ensure the berm itself does not wash away. Option 3 proposes a submerged breakwater located entirely offshore. This means constructing a completely new underwater barrier, out in the deeper water, to break the power of the waves before they ever reach the existing crescent. This brilliantly preserves the crest height and the ocean views. However, building an entirely new offshore structure requires highly complex underwater construction. It demands exhaustive environmental impact studies on water currents and marine life, and ultimately creates a second structure that will also require its own continuous maintenance. If you had to make the decision, would you add thousands of tons of rock to the existing crescent construct, a wider berm, or build a completely new submerged wall out in the deep water? When an island requires a new structure to protect the structure that was originally built to protect it, has the true cost of artificial land ever been fully calculated? The luxury market cannot tolerate a disruption to its aesthetic perfection, but it also cannot survive without guaranteed safety. Balancing these two opposing forces is the ultimate challenge of modern economics. The real question is not whether Dubai has the engineering capability to protect the palm. The technology clearly exists. The real question is whether that expensive adaptation process will ever reach a definitive end. The crescent remains the absolute core of the coastal defense system. The latest modeling does not prove the palm is collapsing into the ocean. It simply demonstrates that both the armor stability and the overtopping limits must be seriously re-evaluated under modeled future conditions. The lower tow and the filter layers still successfully meet the strict research criteria. The island has already undergone a massive beach nourishment operation, but maintaining sand is not the same as a revetment failure. Technical solutions to upgrade the rock barrier do exist, but they all demand fresh materials, significant physical space, complex construction logistics, and new cycles of maintenance. Artificial land is not a static asset. The immense value of the interior real estate is entirely dependent on the ability to maintain the exterior shield. The Palm Jumeirah is often narrated as a completed project. The sand was pumped. The palm tree shape appeared. The luxury villas and Michelin-starred restaurants were built. But looking from the outside of the crescent, the work has never truly finished. The waves are still testing the rocks. Erosion is still altering the beaches, and every new generation of engineers may have to reevaluate a structure designed for the conditions of the past. The palm does not need to sink to become a profound financial burden. It only needs to rely on a defense layer that must constantly adapt alongside the ocean. So did Dubai truly reclaim this land from the sea, or are they merely renting it through a maintenance contract that never ends? Do you think the palm should be heavily reinforced right now, or should they wait for real-world data to show the safety margin has actually decreased? Leave your choice in the comments below, and let me know how you would balance the cost of engineering against the forces of nature. The technical results discussed in this video come from a modeled academic study. The upgrade options are preliminary designs, not evidence of severe current damage, or an officially approved construction project.